Hello and welcome. This is my two-stage rocket-launched experimental glider. We are in Kerbal Space Program with Ferram Aerospace Research installed. Today, and hopefully in a few future videos as well, we'll take a look at the in-editor graphs and calculations that Ferram Aerospace Research can show when designing our crafts. Let's get started by launching this thing. Jeb, we are ready when you are. Launch. Trimming nose up, just a bit. Flamer, staging. Let us accelerate. That was just the fleet booster falling to the ground behind us. We only needed that to launch us the first few hundred meters off the ground. So how fast can we go? We'll do a speed test to see how fast this craft goes, horizontally and with a solid rocket booster hurling it along. This video consists of two halves. The first half is in the flight scene and the second half is in the editor. I have re-recorded the second half and made a new voiceover for the video, but kept the video footage of the first half that you see here. I noticed that we are still in a slight climb. I don't think it's enough that it makes a real difference to the measurement. Okay, now we are a glider aircraft. Actually a glider aircraft, not just by name. Let us commence our right-hand turn and have Jeb set up for an S-shaped approach path to the island runway. If you found this video, then you probably know this game well already. It's likely that you know the Ferram Aerospace Research plugin too. Still, I'm going to introduce both at this quiet phase of the flight. This game is Kerbal Space Program, often abbreviated to just KSP. The game is not new, in fact it had its 10-year anniversary already. Kerbal Space Program and everything Kerbal is the intellectual property of Take-Two Interactive. The latest game version is Kerbal Space Program version 1.12.2, and it is possibly the last version of Kerbal Space Program 1 that we'll see. The sequel, Kerbal Space Program 2, is currently in development. Ferram Aerospace Research is a plugin. We often refer to Ferram Aerospace Research as the FAR mod or the FAR C mod, where the C stands for continued. The continued part in turn refers to the fact that neither the original game nor the original FAR is entirely new at this point. Before I go on, let us have a look at how our flight is progressing. We are, no pun intended, turning on to a far left base for the island runway. Now start our turn toward the airfield and also extend the landing gear. Putting landing gear on this plane is a bit silly, but I've done so because I would like to show off the lower and raise gear functionality in the editor later on. When Ferram Aerospace Research was first created by Michael Ferrera, the inspiration was to create an improved aerodynamics model for Kerbal Space Program, because at the time the aerodynamics model in KSP was quite poor. In defense of the KSP developers, the game was and is about flying spacecraft, so the aerodynamic model likely was not top of mind in development priorities. There's a YouTube video by Scott Manley from January 2013 that shows the great improvement that Ferram Aerospace Research made to Kerbal Space Program at the time. In my opinion, FAR is no longer strictly necessary as far as the aerodynamics model goes, because the stock KSP aerodynamics model has since been much improved. I do, however, enjoy the in-editor calculations and graph that Ferram Aerospace Research gives you, numbers that you do not get in stock KSP. I realize that it's a bit of a strange reason for having FAR installed, but there we go. So about the flight model, one of the slightly odd issues with a quote realistic aerodynamics model is that it highlights the, let me say, fabric of the Kerbal universe. The parts used to create Kerbal vehicles are mainly intended for Kerbal spacecrafts, so they are in many cases heavier than you might think. That in turn means that most FAR airplanes are good gliders that are able to carry a lot of excess energy in the form of extra speed that is only bled off slowly. Maybe you can get an idea of the phenomenon now Watching Jeb's final approach to the runway. We are going to need our wheel brakes once we have touched down. I mentioned that the newest version of KSP is 1.12.2. This, however, is KSP version 1.3.1. I've not yet, at the time of this recording, decided if I want to switch to version 1.12.2. I might. This version of FAR-C is a bit of a hybrid build that I compiled. I think of it as an upgrade to the Lundgren version of FAR. It does not, however, incorporate all of the latest enhancements from FAR-C. The principal author of the FAR-C branch is Damantis Kabolis. There are a lot of Ferram Aerospace Research folks on GitHub. The difference between them is often which topics are the most interesting to their respective authors and the general wider interpretation of how the aerodynamics model best fits the Kerbal universe. Quite obviously, this is not the first time someone made a video explaining in-editor FAR calculations. I remember watching a YouTube playlist by Player Silent Death from spring 2015 labeled Comprehensive Ferram Aerospace Research Tutorial. The abbreviations and even sometimes the logic used to describe the in-editor aerodynamics calculations are not always entirely clear to the unprepared player, and for that reason I would like to make some videos, I don't know how many, to show what the calculations mean by way of examples. Also, there are some textual explanations at my GitHub Wiki pages. Although they are several years old and very infrequently updated, they are there if you want to look at them. Maybe it's time we leave Jeb here to greet the Kerbal press and let him boast about the flight, and we'll head back to the Space Center. I don't want to end this video without having shown at least one calculation. I want to show you a back-of-the-envelope trick to guess at a ballpark figure for the top speed of the glider while being propelled by this solid rocket booster. But first, let me open the FAR settings and tell you why this part of the video is re-recorded. In between the flight and editor scene, I clicked about in settings, trying to decide if I wanted to show configurations options in the part 1 video, and decided not to. For a long time, possibly for years, I had the difficulty settings at moderate area ruling when playing KSP. I guessed I must have set the difficulty back to moderate area ruling out of old habit. The funny thing is that before I went to the flight scene, I made sure to set it to strict area ruling because I felt that might be the more authentic setting for a video tutorial. Anyway, it of course ended up messing up the editor calculation result in the second half of the video. This time I'm leaving the difficulty setting at strict area ruling. Let's get back to the ballpark back-of-the-envelope estimate for the top speed of the glider. In the VAB, Vehicle Assembly Building, one of the editors, we can get a lift-to-drag readout. Remember that we did a horizontal speed test. That means we will be able to assess the accuracy of our ballpark figure by comparing to the real value. Let us check the lift-to-drag readout. We go to FAR, we go to the Stability Derivatives page and click Calculate. Lift-to-drag 3.5, and there are some red numbers there too. Did I not say that FAR airplanes are always good gliders? I did. In this case, because the SPH, Spaceplane Hangar, is the main editor for airplanes, the VAB, this editor, can be a bit finicky about the orientation of the spacecraft being built. With the airplane oriented for a north-up launch, recalculate the lift-to-drag ratio. There we go. Now the lift-to-drag ratio is better than 10. And by the way, by north-up I mean one where the roof of the aircraft is oriented towards the south, so that an ordinary pitch-over maneuver will get us heading north. I just wanted to show that little gotcha. Anyway, what I really wanted to estimate was the empty glide configuration of the airplane, so let us get rid of the unwanted weight here. I know that for a horizontal speed test the booster was not technically empty of fuel. I emptied the fuel anyway because it is easier to just go right at the glider configuration calculations and it will hardly make any difference anyway. Let us do our back of the envelope calculations. The situation when reaching maximum speed is that lift has to be able to carry the weight of the glider. The mass of the craft is 2,846 kilograms multiplied by Kerbal gravity acceleration 9.81 meters per square second, a total lift force L of about 28 kilonewtons. The maximum amount of drag that we can overcome is equal to the propulsion force produced by the solid rocket booster. The thrust of the hammer solid rocket booster is 200 kilonewtons, roughly, multiplied by the thrust limiter setting of our 20% force limited hammer. A maximal drag D of 40 kilonewtons. That will then give us a lift to drag ratio. All in all, it means we should be able to continue to increase speed up to about the point where LD is as poor as 0.7. We did our speed test at 1.5 kilometers of altitude. Lift to drag 8, we can go a lot faster than that. 4.8, we can go faster still. That's 3.5. 1.0, we can go even faster. Oop, that was too much. Let's try 0.75. Still too fast. Let's say 7.2 maybe. We can go faster than 7.2. We can't go 7.4. It is then. So the end result is that our ballpark figure is 243 meters per second, and we see from the replay that the wave value is close to 255 meters per second. Not all that impressive, but there is a reason for that. The editor result is Mach 0.73, but because of the hot outside air temperature when we did the horizontal speed test and consequently the relatively faster speed of sound, during the flight a flight speed of 243 meters per second would have been equivalent to Mach 0.70. In the editor at altitude 1500 meters, the temperature is assumed to be 276 Kelvin and the speed of sound 333 meters per second. In Kerbal reality, the temperature was probably about 25 degrees above standard and the speed of sound, say, 348 meters per second. You could then argue that the speed test topped out at approximately Mach 0.73. On the other hand, I can see how that might be more back of the envelope like than you appreciate. Maybe we should clear out of the editor and go back to the Kerbal Space Center view. Before we end, let me pull up the thumbnail for this video. We usually work with lift to drag, LD. We might as well instead have chosen drag divided by lift though. For our horizontal example, if drag is the same as thrust and lift is the same as weight, then drag divided by lift is the same as thrust divided by weight, which is usually referred to as thrust to weight ratio, TWR. The x-axis here is the Mach number from the in-editor calculation. The y-axis is the resulting calculated lift to drag value expressed as a thrust to weight ratio. Our ballpark figure of lift to drag, approximately 0.7, is a thrust to weight ratio of 1.43. The top speed estimate read from the graph is then Mach 0.73. Despite the errors made, I think that in-editor ballpark estimation is a neat trick, and I hope the calculation has served as a tangible example to illustrate the sort of logic you can apply to the in-editor calculation information. Thank you for watching. I hope I have nudged you to go play some more with Ferram Aerospace Research. Maybe in time I will record another installment in this series. I guess I cannot even call it a series yet. Anyway, if I do record another one, I hope you will stop by and have a look. Best of luck out there navigating the Kerbal sky.